Welcome to the last part of the series Getting Started with OAuth and OpenID Connect. In this session, we'll go through how to use OAuth with single-page applications. My name is Jakob Ideskog, and I'm an identity expert at Curity. Today, we'll talk about what single-page applications, or SPAs, are, and how we can use OAuth with SPAs, how we can use the SSO session to refresh the tokens, and we'll also look at the assisted token flow, which is another approach to obtain tokens for an SPA. Finally, we'll talk about the backend for Frontend. A single-page application stands out from regular websites by not having a backend. It's typically loaded directly from a CDN or a static server, and all its logic resides in the browser. It has no other dependencies to the backend than loading the static resources it needs to operate. It uses history rewrites and local state to keep the perception that the user is navigating through the site. This means that the JavaScript on the site is responsible for communicating with the APIs directly using XHR or fetch. If the API resides on a different domain than the SPA, it's a cross-domain request. This is only allowed by the browser if the API supports CORS, which is becoming more and more common for APIs. What I just described about the SPA and how it accesses the API has a certain implication when it comes to OAuth. It's by definition a public client because it can't hold a secret. Such secret would be part of the JavaScript loaded by the site, which then would be accessible to anyone inspecting the source code. This means it has no ability to authenticate itself against the token endpoint, since it can't hold a secret to prove its own identity. Other things to be aware of is that SPAs, even more than regular web clients, are susceptible to common OWASP attack vectors, such as cross-site scripting attacks, CSRF attacks, and just the mere fact that the access token will be available in the browser, since the browser is the one now making the requests against the APIs. This means that a cross-site scripting attack, if successful, could now obtain the bearer token it needs to make API requests on the victim's behalf. Using OAuth with an SPA is not tricky in itself, but it's necessary to be aware of how it should be used to avoid unnecessary exposure to attacks. So before we dig in too deep, we should take a look at the implicit flow. This has not been discussed before in this series, but it's a flow that was part of the original OAuth specification. It was intended for these types of applications, but that suggestion has later been updated to use the code flow instead, as we'll see later. But it's useful in some cases, and it's good to be aware of. The implicit flow is entirely run in the front channel, so it starts by calling the authorized endpoint like the code flow, but with the difference of setting the response type to token. This toggles the authorization endpoint into the implicit flow mode rather than the code flow mode. As usual, the user is prompted for authentication if necessary, and once the user is authenticated, the authorization server redirects back to the callback endpoint of the application. In a single-page application, this will load the same application again. The big difference from the code flow is that the token is now returned immediately in the fragment part of the callback. The fragment is not passed to the backend by the browser, but it is intended for code running inside the browser. The client was not authenticated, but instead the flow relies on the user authenticated and that the client is in possession of the redirect URI. There is no refresh token issued in this flow. The problems to be aware of is primarily that the token is passed directly in the URI, which leaves it visible for both the user and code running in the application. But more on that later. Let's continue with the code flow. If you watch the OAuth for mobile applications video in this series, you'll recognize much of what we'll go through here. As always, the client starts by sending the user to the authorized endpoint of the OAuth server. It passes on the client ID and other necessary parameters for the code flow to begin. The OAuth server redirects to the authentication service, which in turn lets the user authenticate. Once the user has authenticated, the user is redirected back to the client. Now this means that the same application is loaded again and we can pick up the response from the query string. No backend is involved in reading the parameters of the callback. The SPA now picks up the code from the query string and makes the post request to the token endpoint. Here things are a bit different. The post is now a CORS request, unless the OAuth server is on the same domain as the SPA, which is unusual. Since the client is a public client, it cannot authenticate itself, so it only passes its client ID, and the OAuth server is configured to allow the My App client, in this case, to perform a token request without authentication. The code is verified, and the OAuth server returns the access token to the client. By default, OAuth servers using public clients should not issue a refresh token, even though it's both possible and allowed, but we'll get to that a bit later. Now that we have the SPA version of the code flow fresh in our minds, let's look at some attack vectors and what to do to mitigate these. So this is not an exhaustive list of attacks, but it captures the most common pitfalls. Also, many of these aren't just applicable to SPAs, but websites in general. So the countermeasures discussed here are good practice for both regular web applications and SPAs. OWASP has other names for these, but I wanted to make it a bit more clear on what we mean when discussing them. So we have the unsolicited callbacks, we have the history traversing, the access token interception, and ID token forgery attack vectors to look at. So let's start with the unsolicited callbacks. There are variants to this, but they follow the same principle. The idea is that an attacker, Eve, somehow can trick Alice into starting a flow on the evil side. Let's assume Eve makes a site, evil site, and gets Alice to visit that site. Alice is tricked into clicking a link on the evil site that leads to the good site. Before she is sent over, Eve makes an authorization request to the authorization server where Eve authenticates. Eve takes the nonce and puts it in the request over to the good site. The request is shaped as the callback from the authorization server, so good site automatically takes the nonce from the URL and redeems it against the authorization server. Without knowing, Alice is now logged in to good site, but has Eve's access token in the browser. So any operation she makes will be against Eve's account rather than Alice. This is also called a code injection attack and can come in a few flavors. The key takeaway is that good site accepted the redirect to the callback endpoint and automatically redeemed the code. It didn't check that this was a callback for a request it had started itself. There are two ways to mitigate this attack, either using the state parameter or by using the proof key for code exchange mechanism, or PKCE. Since the advent of PKCE, it is the preferred approach, since it leaves the state parameter to the application for other use, such as actually keeping track of the application state. The PKCE mechanism was also described in the OAuth for mobile applications episode and works by having the client generate a random secret before it makes the first authorization request. The secret is hashed, and that hash is passed as the code challenge parameter in the request along with the hashing method used. Later, when the application receives the callback and is about to redeem the code against the token endpoint, it needs to add the plaintext key as the code verifier parameter in that request. The token endpoint will verify that the hash of the plaintext verifier matches the hash sent in the authorized request earlier, and only issue tokens if that's the case. This stops any unsolicited calls to the client application from being able to redeem tokens. The client application can of course also check that it has a state with the current key before even making the request. It's recommended to configure OAuth servers to require PKCE for public clients so that there are no paths left open where it's possible to do the code flow without the verifier. It's recommended in general to use PKCE together with the code flow. The next thing to be aware of is history traversing. Since a few years back, browsers opened up the history API. This means that it's possible for applications to read the history and retrieve information therein. If the implicit flow were used, the token would be placed directly on the fragment of the redirected client application, leaving it possible now for other applications to retrieve it if the browser allows it. The current recommendation to mitigate this is to use the code flow instead, and of course with PKCE enabled. Access token interception or stealing is an artifact of the fact that OAuth access tokens by default are what's called bearer tokens. This means that the client using the token doesn't have to prove that it's allowed to do so. It's enough to send the token to the in the authorization header to use it. Therefore, if the client application sends the token to the wrong place, it can be picked up and used without the user knowing. For SPAs, this presents an issue because of the way programmers like to do things. If a token always should be presented when making API requests, it may be injected in a pre-flight stage of the request library. If care isn't taken, this could accidentally lead to the application sending the token to any API it communicates with, not only the one it was intended for. The mitigation is simple. Always check the host URL of the request before injecting a token to make sure it's only injected when communicated with the API it was intended for. The last attack we'll discuss here is forgery of ID tokens. In both the implicit flow and OpenID Connect hybrid flow, the ID token is passed on the URL in the callback to the client application. If we use the unsolicited approach mentioned before, or simply by manipulating the attacker's own browser, we may be able to inject another ID token than the one returned from the authorization server. The site can thus be tricked into believing that the user in the ID token is the one that just logged in and set up a session thereafter. If the client application omits to verify the signature of the ID token, which it may very well do because it believes it got it directly from the authorization server, the attacker can simply create its own token and pass them along. If the client does verify the signature, it may still be susceptible to a stolen token being presented instead, letting the attacker assume the identity of the victim. There are a few ways to mitigate this attack. If you can, use the code flow with PKCE, then the ID token is passed from the token endpoint and not in the callback. If you still need to pass it in the front channel, you should use the nonce parameter. Just like PKCE, the client generates a random identifier and places it in the authorization request. The server will place that nonce in the ID token so the client can verify that the ID token is the one that belongs to the original request. This is required by the OpenID Connect specification when passing tokens in the front channel, but it's not certain all implementations of OAuth servers follow that. With Curity, it's not possible to obtain an ID token on the front channel without using the nonce parameter. Finally, always verify the signature to make sure the token is signed by the party you expect. So let's take a look at the code flow for public clients in OAuth tools. So we'll start a code flow, and we'll use a client that doesn't have a secret. So it's a public client now. We can still ask for scopes if we want to. And let's just run it regularly and we can see the request URI as usual. So we'll start it. We get prompted for login. But now we got a failure back. So it says invalid request, code challenge required. So the OAuth server rejected this public client because we didn't use PKCE, which is as it should for public clients. So let's add PKCE here in OAuth tools and look at the request again. Now we can see two new parameters. We have the code challenge here, which is the hash of the verifier that we generated. It's uniquely generated per request by the client. We can also see the code challenge method, SHA-256, which we pass along so that the server will know how to verify the plain text verifier in the next request. So if we run this now, we're already logged in, so went really fast. And now we see we have a code, and we need to verify that. We're going to send it as in the post body here, so we send the client ID here, and we see the code verifier now as the plain text value of the hash we sent before. So let's redeem the code, and now we got an access token. By default, we don't get a refresh token, as I explained earlier. It's not forbidden to use refresh tokens, but instead the SSO session could be used. Since the client is public, the refresh token is also a bearer token, so it introduces some risk to use it. If you do, however, then make sure to keep its lifetime reasonably short and that it's replaced with a new one each time it's used. The default lifetime in Curity is 1 hour, and it's default that it's being replaced when it's used. A better approach in some cases is to rely on the SSO session and that new session management in OpenID Connect. We won't go through the session management in this series, but let's look at how to use the SSO session. The first time the user logs in, a session is created with the login system. This can be referred to as the SSO session. It's represented as a cookie on the login system. This was discussed earlier in this series. This means that the next time the user needs to be authenticated, it will just get a redirect back because no user-facing screen was presented. The user had already authenticated previously. OpenID Connect has a parameter to control the behavior of this called the prompt parameter. If we set prompt equals none when requesting a new code, the server will respond with an error if the user needs to be prompted for some reason. With this, and if the server allows it, we can do the flow in a hidden frame. If the server responds with a code, a session exists, and we can redeem it for a token. If the server responds with an error, we need to restart the flow in a way that the user can interact with it, either in a visible frame or preferably with a regular change of page so that the user is aware of what's going on. So let's run this flow again, and let's make sure we're logged out. So now, in order to check if we're logged in, or at least try, we can run this flow with the prompt equals none parameter, and we can make sure we run it in a frame this time. OAuth tools won't run it in a hidden frame, but we'll run it in a visible frame, but you'll see it. So let's start the authorized part of it. It immediately aborted and said authorization endpoint failed, login required. So we could catch this error and break out of the hidden frame or make it big frame and restart the flow. So now we know there was no SSO session the user needs to interact. So we need to remove the prompt parameter in the next request and run it again. So we can still run it in a frame like we do here, and this will overlay the site you have. We log the user in and we redeem the code for a new access token. Now that we're likelier to have an SSO session, let's try again. Prompt equals none and run the first part. Yes, no error. Redeem the code, new access token. So this way we can work with hidden and visible frames, or hidden frames and full redirects to the page if we want to be able to get new tokens, relying on the lifetime of the SSO session at the login system rather than a refresh token in this case. Another flow that's currently in a proposed draft is the assisted token flow. It solves the problems of the implicit flow by always using frames and communicating with post messages instead of the redirect URI between the client application and the OAuth server. The client always opens a frame and starts the assisted flow. The assisted endpoint is similar to the authorized endpoint but requires fewer parameters. The flow relies on SSO for refresh, just like I explained for the code flow. However, when the assisted endpoint communicates the error back, it sends a post message to the client. This provides a convenient integration method when frames are possible. If the assisted endpoint reports that authentication is required, the library will abort the flow and start a new one in a visible frame instead, where the user can log in. There are fewer calls to the OAuth server compared to the code flow, and the response is not passed in the URL as with the implicit flow. Lastly, we should mention another approach, the backend for frontend approach. Even though SPAs don't have a backend, sometimes that introduces more risk than may be comfortable. In such cases, you can deploy a small backend for the frontend. This is a stateless component that is deployed with a secret. This turns the otherwise public client into a confidential client. Refresh tokens can be used, since now the backend is the one that performs the refresh. The tokens can be stored encrypted in a secure and HTTP-only cookie that only the backend can read. This provides a stateless backend with no external dependencies. When the client needs a new token, it needs to call the backend for frontend to start the flow. And when it's done, it must receive the token from the backend. To wrap up, we should mention that we haven't discussed how to store the token in the SPA that don't have a backend for frontend pattern. There's no silver bullet, but common practice is not to use a storage mechanism that can result in other applications retrieving it. The session store is useful since it's not persisted between browser restarts. Another approach is to store it in application memory, which is a bit more volatile. And finally, when dealing with SPAs, always remember that the client is public, even if you use a secret in the front end. It should be treated as public by both the developer designing it and the OAuth server communicating with it. This is the end of the Getting Started with OAuth and OpenID Connect series. We hope you learned a lot. If you have any thoughts or questions, don't hesitate to contact us. Thank you for listening.